So I'm very happy to be here to present our work. So that was in collaboration with my wonderful colleagues and PhD students from University of Surrey and Royal Holloway, University of London. So the motivation for this work is persistent memory. So the persistent memory devices or non-volatile memory devices have been around for a while. And more recently, there is a new generation of such devices are upcoming, which are 6-cell based. And non-volatile memory is great. So it is byte-addressable. It is fast. So it is it's not as fast as DRAM, but close to that. And it offers an opportunity for a much faster durable system. So by durable systems, I mean systems that can recover consistently in the wake of crash. However, developing crash-resistant applications on top of NVM correctly and efficiently is not trivial. So the reason for that is that NVM essentially behaves as a weak memory. That means that if we don't take care of explicitly flush caches and insert memory barriers as necessary, then it is possible that the information that's going to be stored on NVM won't be enough to be able to recover in the wake of crash. So to illustrate, here's a simple program that just enqueues n items into a ring buffer. So this is quite straightforward, and it works fine if the ring buffer is on DRAM. However, if I want to make this ring buffer crash consistent, then I need to do some work. So I need to include some flushes and fences. And the problem with that, of course, is that if I use too many of these instructions or I use those which are stricter than necessary, then that would degrade performance. So for example, if I replace the first flush here with fence, that's still crash consistent, but it would run much slower. On the other hand, if I don't use sufficiently many instructions and I don't put them in the right places, that the program won't be crash consistent. So for example, if I remove just one fence from this program, it won't be able to recover correctly in all situations. So failure atomicity libraries have been introduced to address this programmability problem. And these have primitives, high-level abstractions, such as failure atomic sections, persistent transactional memory, that aim to simplify development of crash-consistent applications and systems. And if I want to rewrite the program that I showed before with using a PTM, it would look something like that. So you can see that this is still non-trivial, and the development effort is still not negligible. And in particular, I have to be able, as a programmer, to identify exactly which sections of my program need to be failure atomic. And I also need to instrument every store with this additional call that would essentially adds a range to the transaction. So ideally, what I want is something which is transparent, right? So what I mean by transparency here is that I start from a volatile application or data structure that is correct if it is not persistent. And then somehow I convert it to a failure atomic one. Hopefully I invest minimum programming effort and performance overhead in doing so. So the systems like that have been proposed. So the two prominent examples are Pronto and Persimmon. So what these systems say is that instead of asking the developer to explicitly tell us which regions need to be failure atomic, basically say that, okay, so let's assume that the public API requests is my failure atomicity granularity. Okay, so I want to provide failure atomicity for every request in public API. So then there are essentially two main components to this system. So one is the request log on non-volatile memory. So every request that comes into the system, it is executed on the online DRAM copy of the application. And also, if this is a read-write request, it is logged on NVM. And then there is also a mechanism to persist the request effects on NVM, so we can truncate the log. And there are different techniques to do this. So Pronto uses snapshots. Persimmon uses shadow executions. So what are the key limitations here? So first limitation is that these frameworks are not completely general. So in particular, they don't allow non-deterministic requests. And the requests must be deterministic because what is logged are requests and not the effects of the request, for example. So that means that if a request is non-deterministic, if it is re-executed upon recovery, then the result can be different from the result that was obtained when it was executed on the online copy. Also, there are other limitations that, for example, Pronto imposes such a state can only be modified through the public API. So that in particular disallows global variables. So another limitation is the performance overhead of processing, log, and snapshotting. And this is particularly serious for large working set sizes and high update ratios. So in this work, in our work, we set out to address these limitations. So our system called Mangosteen, and it provides fast, transparent durability. And main points about it is that it is first, it is general. It supports non-deterministic requests, global variables, and everything else. It is easy to port an existing volatile application to Mangosteen. There are just 6 developer-defined callback functions that need to be implemented. And those are typically just simple wrappers around the existing application code. And if you are interested to see a specific example, there is a detailed example in the paper how to port an application to Mangosteen. So the centerpiece of the Mangosteen design in the concurrency control, which is co-designed with durability. And this allows us to minimize performance degradation across all update ratios. So let's dive in and talk a little bit about the Mangosteen implementation. So the architecture of Mangosteen consists of a front end and a back end. So the front end is in DRAM, and this is shown in blue, and the back end is in NVM, and it's shown in yellow. So the application request comes in, and then it gets intercepted by our NVM-aware concurrency control. And that uses the callback implemented by the application to execute request on the online copy. So now comes in the main difference of Mangosteen from the previous systems is that we instrument this run in memory in order to intercept write instructions. And this is done only for read-write requests. So read-only requests just execute without any instrumentation. So these write instructions, they come back to the concurrency control, and then they are deduplicated, they are compressed, and then what is written to the redo log on NVRAM is just compressed batches of these elementary write instructions. Okay, so the amount of information that we write on the redo log is typically small, and this is just the effects of the request. So in particular, that allows us to implement, to support non-deterministic requests. So in addition to that, there is a log processor mechanism that takes the runs in the background and takes the write instructions from the redo log and applies them to the state on NVM. Right. So now I want to concentrate more on the concurrency control. So because that's probably the most novel part of our design. So, so here you see this spider. So the spiders are cores, and what I show here, so the concurrency control runs on the front end, and those are cores. So we have a thread per core which process the incoming requests. So the when core receives a read-only request, it tries to acquire shared lock, and once it acquires shared lock, it just goes ahead and executes it on the online copy of the application. And all these requests can be, all these read-only requests can be executed concurrently without any limitation. Okay, so we have unlimited read-read concurrency here. So the processing of read-write requests is more subtle. So what we use here is the technique known as flat combining. So how we use flat combining? So there is this advertisement table which has an entry for each core, for each thread. And then when a thread gets a read-write request, it does not execute it, but it advertises it in this table. Then what happens is that the threads try to acquire an exclusive lock, and the thread that succeeds to do so becomes a combiner, and the combiner would execute this request sequentially on the application image. And this runs under dynamic binary instrumentation, and we get out of this a stream of instrumented write instructions. So the next step here is address deduplication in order to reduce the amount of data that we log on the persistent memory. So, so note that we don't need to instrument reads because combiner runs under the exclusive lock, so there is no any interference from other threads that can potentially write concurrently. Okay, so our address deduplication mechanism works as follows. So we represent DRAM logically as a sequence of regions of the size 32 bytes. So when we get the write request, we identify the regions that have been touched by this request. And then we use a hash table to insert the addresses of these regions into the hash table. So this way we can deduplicate the accesses, right? So, so in this case, there are 3 addresses that have been touched. So this address is already in the hash table, so it gets deduplicated. This one as well. So this one is new, so it is inserted into the hash table. Okay, so this is how address deduplication works. So after address deduplication finishes, the next step is to persist the data that has been referenced by addresses in the hash table to the redo log. And note that at this point, we have the latest version of the modified regions available in DRAM, right? And this is, again, due to the benefit of an exclusive lock. So what happens here is that how persistent logging works. So we just essentially just take the addresses that we stored in the hash table, we add them to the log. So the log is implemented as persistent ring buffer. So when we do this, we write sequentially to the NVM, which is the most efficient way to work with it. It maximizes throughput. Okay, so after we did it, we execute one fence, and then we advance the tail, and then we execute another fence. And this is great because we only have 2 fences per batch on the critical path, right? So the fence is it's very expensive for NVM, and we have to minimize their number. Okay. So after this is done, then the threads can return back to the applications with the response because everything was persisted. So just to summarize the benefits of concurrency control and durability co-design. So on one hand, we maximize concurrency where it matters most. So we achieve unlimited read-read concurrency. And on the other hand, we minimize interference where it matters most. Okay, so we maximize throughput of the persistent media. And that allows us to use NVM in a sequential manner, which is efficient. It only so persistent only requires constant number of fences on the critical path. We have low instrumentation overhead because we don't instrument reads, and we are able to conserve bandwidth using deduplication. Okay, so let's talk about evaluation. So in the evaluation, we are looking to address the question, what is the overhead of transparency? So for this purpose, we implemented 2 case studies. So our main case study is Mangosteen-based version of Redis. And the second case study is the key value store, which supports LevelDB API. And we used 2 benchmarks to evaluate our case study. So we used YCSB for Redis, and we used LevelDB benchmark for key value store. So I will talk about benchmarking Redis. And in the paper, we will have much more information about the other benchmarks and other performance studies that we conducted. So what we used is a pretty standard Ubuntu server with 128 gigabyte of DRAM and 1 terabyte of Intel Optane persistent memory. So let me start by showing you the baseline. So here we examine the peak throughput as a function of update ratio. So you have update ratio on the x-axis and the throughput on y. Okay, so what you see here is Redis and Persimmon. And what is interesting here is that is this drop in the Persimmon performance, which occurs at higher update ratios. And this is because of the overhead of persistent logging and processing the persistent log. Okay, so now let's put Mangosteen on the same graph. So what we see here is that we improve against both vanilla Redis and Persimmon across all update ratios. And the reason we improve in this area where update ratios are low, so this is read-only, mostly read-only workloads, is because of read-read concurrency. And this improves the baseline Redis as well, because Redis is not concurrent, it is sequential. But even more interestingly is that we also improve here for high update ratios, and we kind of have a graceful degradation of throughput as update ratio increases. And this is because of this co-design of concurrency and persistence and optimized persistence. So we also evaluated the duplication effectiveness. And here we look to see, so what happens if actually the effectiveness of the duplication depends on the distribution of keys in the workload. So to check that, we used one workload with zipfen key distribution, another one with uniform. And the red line is performance of Mangosteen without the duplication, the green line with the duplication. So the performance for zipfen workload with the duplication is better, and it becomes better as the update ratio increases. That's not surprising because the duplication is only at work when we have read-write requests. And but what is interesting is that we also improve for uniform key distribution. And the reason for that is that another effect of our deduplication mechanism is that we are able to coalesce adjacent writes into these regions that we are persisting. And because of that, we also get improvement on the uniform. Okay, so this is those are two performance studies that I wanted to share with you, and there is much more in the paper. And let me just conclude. So transparency is important, but supporting transparency for a persistence comes at the price of performance degradation. And the solution that we came up with is co-designing concurrency control and durability. And by doing so, we're maximizing concurrency where it matters most for read-read request, for read-only request. And we are minimizing interference where it matters most, right? So by minimizing interference, we have an opportunity to access NVM sequentially, maximizing throughput, use constant number of fences on the critical path, have low instrumentation overhead by not instrumenting read instructions for read-write request, and conserve the write bandwidth via deduplication. And we have artifacts available, and thank you for your time.